Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we're going to start considering phase equilibrium for binary systems at higher pressures. And in particular, we'll be looking at the Konynenburg and Scott classification system for binary mixtures. So our goal is that you will be able to at least recognize the possible phase equilibrium behaviors for binary mixtures based on the Konynenburg and Scott classifications. So in general, let's just start saying we have two pures, so this is component 1, and its critical point is here for component 1, and for component 2, the critical point is right here. As I combine mixtures 1 and 2, what's going to happen is I'm going to continue to have two-phase behavior. Remember, this is the vapor pressure curve. So therefore, I have liquid plus vapor in equilibrium here. And as I add a little bit of component 2, I will continue to have mixtures of these two components and two phases. But the reality is that I will sometimes find that these new vapor pressure-like curves will stop, okay, perhaps short of actually making a full span of the compositions, and we've already talked about that. But as you look at these, and if you take the end point, the highest pressure and temperature that these various mixtures, in a type 1, a nice mixture, if I do these various things and look at where I get this vapor-liquid split and plot where these points go, I'll see that the highest pressure and temperature, the critical point for these binary combinations, traces out a curve that extends from one critical point to the other critical point. This is called a class 1 system by Konynenburg and Scott. And this is probably the easiest type to make sense of. And this curve that we trace out here is the critical points for the various combinations of the composition for between component 1 and component 2. An example of a system that does this is CO2 plus normal butane. So what about the other systems? Let's take a moment and look at some of those. So class 2. In class 2, what we're going to find is that I have very similar systems, that I'm going to have my vapor pressure curves for my two pures. They end at a critical point. And if I do various combinations of mixtures, I end up tracing out a curve where I have the critical points for the liquid plus vapor mixture. Okay? But in some systems, and an example would be CO2 plus normal octane, in this system, I'm also going to have other combinations where I'm going to have the liquid splitting into two other phases. And typically, I'm going to find, and I wish to, let's change colors here. So blue is going to be liquid plus a different liquid plus a vapor. Red is going to be a liquid plus a vapor. And what I have is I have these points here that are liquid plus a vapor. And this is going to end at a critical point of a sort, okay? This is usually called, well, we'll get to that in just a moment. But anyway, this will terminate, and after that, I will no longer have this behavior. Now, these are going to be different sets of combination or sets of compositions than I was getting in this red liquid vapor curve. Okay, remember there's an implied depth to this graph that's composition. Now, the other possibility is that from here, I may not have the vapor phase continue on. It's possible that in some possibilities I will have the two liquids combine and then have liquid plus vapor, anything in this region here. But in other cases, I may have the vapor phase be the one that disappears, and I'll have two liquids that are in equilibrium. Okay, so I'm going to use this green, which is not going to show up in my on my green background. But so on the white diagram, I'll be using green to represent two liquids in equilibrium with each other. And this is a typical system that one might also see where you begin to see three phases in equilibrium. So let's look at what else can happen. This is a class 3 system. CO2 and a rather rare chemical, squalane. I am not sure I've ever actually physically encountered this chemical, but this is one where what happens is you go from this critical point and it begins drawing the same curve like what we just were looking at. It looks like it's headed over to this critical point, but instead it makes a detour. And over here, really this becomes liquid plus liquid. Over here, it was liquid. I don't know if it's prime or double prime. Based on what I'm doing double prime for the higher pressure or higher temperature, temperature, second liquid. And over from this point, I'm going to have an L plus G, and it also is going to look like it's trying to come out here, but it just misses. They don't connect. These two ends do not connect. Okay? Instead, what's going to happen is this is going to bump into that three-phase curve. And when I end up with this happening, this point here is called a K point. Now this doesn't happen very often, okay? It's fairly rare. This system on this curve is L prime plus G. This one is L double prime plus G. They look like they're going to hit each other. They miss, and instead this gas becomes liquid. Becomes liquid-like. And we end up with a system that's two liquids with no gas in equilibrium. Okay, this is a class 3. It's a little more unusual. So let's look at a class 4 system. Carbon dioxide and nitrobenzene is an example of a system like this. Now, I'm going to draw some things and then I'm going to start erasing. So we'll start with looking at our liquid plus vapor system. And like we had before, I have one that's going to come up and it's going to terminate in a K point, where here I have liquid plus a second liquid plus my gas. And I have my L prime plus my gas here. And then from this critical point for my pure, I have one coming over here, and again, it's going to miss. But let's just envision this curve here. If I started to pull down this swinging portion of this graph, and let me pull it down even further. Now at this point, it actually cuts through here. In fact, it does literally cut through there when you see this sort of behavior. And I have a gap in this liquid plus liquid system, liquid plus vapor system. So I have liquid, liquid, vapor here and here, but I have a gap in this region. I still have my K point where the liquid plus vapor come together. Up here I'm going to call this liquid plus vapor, but this is the second liquid. And this last piece here really should be colored green, because this is where I end up with two liquids. Again, this system here would be an example of something that would have this sort of behavior. So let's look at class 5. An example of class 5 would be ethane plus ethanol. In this case, I have my vapor liquid system from the lower temperature pure. I have my vapor liquid system for the higher one. It's going to come down, but what's going to happen is it's going to intersect at a lower terminus, and the curve is not going to continue. There's not going to be a second piece. So this vapor liquid system is going to intersect with the vapor liquid liquid system on one end, and this liquid vapor system intersects on the other end. So this is an example of a class 5 system. Now we have one final type. This is a class 6. An example of this would be CO2 plus naphthalene. In this system, we start out, we have our lower temperature pure material and the low liquid vapor region. I have my liquid vapor. But in another possible thing that can happen, and with CO2 plus naphthalene you observe this system here is going to come up and terminate with another system where I'm going to have my two liquids that come together. And in this case, this point up here is called an upper critical endpoint. And you can think of it like the critical point of the critical points, okay? It's the highest pressure and temperature where this phase equilibrium behavior is still going to be seen to exist. It's not going to continue indefinitely. It's all going to terminate, and we're going to just have a single phase beyond there. So this concludes our brief discussion on the von Konynenburg and Scott classification system. Thank you very much for your time.